Waveguides, Fields and Waves in Circular Waveguides, series on Microwave Engineering, lecture number 1.31. We started the analysis of circular waveguides. We completed one session on that particular task. This session is continuation of that session, previous session. In the present session, the focus is on finding longitudinal components, Ez and Hz, with the help of wave equations. It is step 2. In step 1, basically what we did is expressing transverse components in terms of longitudinal ones. In the present step, second step, we estimate longitudinal components with the help of wave equations. Okay, what we do here right now? We consider wave equation for a longitudinal component. Wave equation is a differential equation. When we solve a differential equation, first what we get is general solution. Here, the general solution is obtained using a method. It is called variable separable method. Wave equation is an ordinary. It is not an ordinary simple differential equation. It is quite complex, multi-dimensional differential equation for which solutions are not readily available. So we have to have a special approach, specific approach. That approach is using variable separable method. Once solution is obtained, general solution, it is general solution. It involves several constants, arbitrary constants. Using boundary conditions, those values to those constants are to be fixed. So boundary conditions are required. Once with the help of boundary conditions, values to arbitrary constants are fixed. It results in specific solution. Here one point of caution is one can start with a wave equation for some other component also, for which boundary conditions are available. Procedural steps remain same to get the solution. What does it mean? See, what we require is right now Ez and Hz. Boundary conditions are available on Ez. Boundary conditions are not available on Hz. You can solve wave equation in Ez, you get general solution, boundary conditions are available, then you get specific solution, successful. We are successful as far as Ez is concerned. But when you try to find out Hz, okay, we consider wave equation in Hz, we solve, we get general solution, but boundary conditions are not available on Hz. Then how to get specific solution? The solution which we want, or the solution which is applicable to the configuration that is on hand, that is particular solution. How to get it? As boundary conditions are not available, how to get it? A way out is, what he is telling is, a way out is, instead of Hz, you can consider Ex, we are in cylindrical system, you can consider rho component or phi component of E, on which boundary conditions are available, and solve the equation. Ultimately, you will be getting Hz. You solve, let us say, you have considered euro, because on euro you have boundary conditions. You solved it euro. From euro, you can revert back to Hz. Okay, that's what he's telling. It's also possible. We are going to see anyway. Step 2, procedures. So that is starting point, and then actual process is, first the wave is assumed to be Tm. With Tm, Hz is 0. And we found solving wave equation. Ez is found solving wave equation. Once Ez is available, anyway, we started with Hz equal to 0. Now we have both Ez and Hz available. We substitute these two expressions to find H rho, H phi, E rho, E phi. That ends the problem, solution. That gives us the solution which we wanted. Next, the wave is assumed to be T. Ez is 0. T means Ez is 0. Hz is found solving its wave equation. Then we have Ez, we have Hz also. With the availability of Ez and Hz, you can find out H rho, H phi, E rho, E phi. Now all the field components are considered to be known, available to us. Third step is, or third part of this session is, we assume the wave is a hybrid one. Because it is hybrid one, Ez and Hz both are non-zeros. One can solve wave equation for Ez and Hz to find Ez and Hz. Once Ez and Hz are available, they can be substituted to find H rho, H phi, E rho, E phi. So that is third part. In the analysis, we have seen boundary conditions are required. When you solve wave equation, first what you get is general solution. From general solution, we obtain specific solution. Specific solution or particular solution is the one which is specific to the configuration under consideration. General to particular solution requires boundary conditions. The boundary conditions in case of circular waveguides is at rho equal to A. The inner surface of guide exists, so tangential component of the electric field must be 0 there. Therefore, E phi Ez must be 0 at rho equal to A. See, we have placed the waveguide like this. This is Z. It is assumed that radius is A. This is rho. So at rho equal to A, what you have is inner surface of the conductor. This is conductor. The conductor is assumed to be perfect. Therefore, tangential component of electric field at the surface of a perfect conductor is 0. Here tangential components are 2. One is phi. Phi is tangential. Z is also tangential. See, phi is like this. This is phi. Z means upwards or downwards. So these are tangential to the surface. So they must be 0 at rho equal to A. This is the boundary condition available. We are going to use it. Now to begin the first wave, we consider is a TM. TM wave, Hz is 0. So Ez, we estimate Ez. For that we consider wave equation. It is expanded. Note we are in cylindrical, so the expansions are slightly complicated. They are complex, they are complicated. Here, dou square Ez by dou Z square. Actually, here the term that exists is dou square Ez by dou Z square, but we know pretty well wave is traveling in Z direction. As a consequence, dou by dou Z is minus gamma. Dou by dou Z becomes minus gamma. So it is replaced, so resulting this. Now a little bit of manipulation, moving terms this side, that side. It results in introduction of H square. Here H square is, as already mentioned, it is gamma square plus omega square mu epsilon. So this equation is quite complex. Direct or straightforward solution is not available. There's a technique got developed. It is called variable separation method. We apply this method. According to this method, we have to assume Ez equal to product of two functions P and Q. P is function of variable rho alone. Q is function of phi alone. Here one point is required to be mentioned. Where is the guarantee that Ez is specifiable as product of P and Q, P function of rho alone, phi, Q function of phi alone? There is no guarantee. There is no guarantee, but it's only a possibility. See, as it is, solution is not available. This is the point, basic point. So then what to do? A way out is suggested, that is using variable separable method. This method is possible only when Ez is product of two functions, each function being one variable dependent. So this much is also not possible. This much solution is also not possible if Ez is not expressible as functions, product of two functions with a single variable. So it's only a possibility. This method gives you a possible solution, right? Now substitute Ez equal to PQ, resulting in this equation. This equation is split into two equations, one in P and one in Q. So it involves P as well as Q. It is split into two equations, one in terms of P, one in terms of Q. Of course, this is standard equation. Equation in Q is a standard equation. Solutions are readily available, but this is highly complex. In fact, no solution is available. No closed loop solution is available for the equation that is in P. Solution of first one is JNHA, Bessel function. JNHA. JNHA is a function. It is a series. In fact, JNHA represents a series. It is not closed loop solution. And the second one is, for the second one, solution is AN cos n phi, BN sin n phi. This is second order equation. Simple equation, ordinary equation. Solution is readily available. So now Ez is PQ. Therefore, this is general solution. To obtain specific solution from general solution, we have to use boundary conditions. Ez is 0 at rho equal to A. So implementation of this boundary condition results Ez equal to Jn rho H&M. Here it is rho H. Now here rho H&M cos n phi. Of course, these are Z variations. These are time variations. Listen carefully. Here arbitrary constants are 3 are there, but boundary condition is 1. So one boundary condition, fix value, give value to only one arbitrary constant. In the present situation, Ez equal to 0 at rho equal to A, which is the boundary condition. In fact, it fixes the value of H. An value cannot be fixed. Bn value cannot be fixed because one boundary condition, how can it fix three constant values? It is fixed. It is fixed. H is fixed to HNM. HNM is HANM by A. Here HANM are roots of Bessel function equation. This is called Bessel function. Equal to 0 is Bessel function equation. Now, after obtaining solution Ez, we can substitute this expression for Ez. Already we are having Hz equal to 0. These two we can substitute to find out H rho, H phi, E rho, E phi. Now let us consider the case where the wave is TE. Next we consider the wave TE, not TM. TM we have completed. Let us say the wave is TE. Therefore, Ez equal to 0. Now wave equation is solved for Hz. Del square Hz equal to minus omega square mu epsilon Hz is the equation. This is very much similar to the wave equation which we have in case of Ez. Only difference is E has been replaced by H. Therefore, the solution of this equation, del square Hz equal to minus omega square mu epsilon Hz, the solution of this equation is going to be same as the solution of the equation which we encountered in case of TM wave. Only thing is E has to be replaced by H. So this equation is similar to one considered in case of TM wave, and hence general solution must be same as TM wave solution. As far as general solution is concerned, up to that point is concerned, nothing to worry much, but from general solution to obtain specific solution, we have to implement boundary conditions. But boundary conditions are not available on Hz. That is the problem. As boundary conditions are not available on Hz, what we do is, first we get E phi. How E phi is obtained? Hz is available. General solution of Hz is available. Using that expression, we obtain E phi on which boundary conditions are available. Then we apply boundary conditions on E phi. Certain constants disappear, or certain constants values gets fixed. Okay, that is the way. Applying the boundary condition E phi equal to 0 at rho equal to A. Ultimately, what we get is Hz is equal to An prime. It is an arbitrary constant. Jn rho H prime nm cos n phi e power minus j beta bar z e power j omega t. Now there is one more expression for H valid for TE waves. It is H equal to HA prime nm by A. This fraction is called H prime nm. Here HA prime nm or HANM prime are roots of Bessel equation. J prime n HA equal to 0. He is telling one more expression. What is this one more expression? Already we have an expression in the form of characteristic equation. What is that? H square equal to gamma square plus omega square mu epsilon. This is the relation for H. It is derived in the first part of the analysis of circular waveguides. This is called characteristic equation. Okay, so this is one expression for H. Now we have another expression for H. H is HANM prime by A or HNM prime. This is another expression. Of course, this expression is valid for TE waves. Now once we have Hz, Ez anyway 0 for TE. Now we have both Ez and Hz. We substitute and find out H rho, H phi, E rho, E phi, getting all the components. One can notice the solutions of the fields in circular waveguides. They involve Bessel functions. Here are shown graphical representation of Bessel functions Z0, J0, J1, J2, J3. One or 2 points one can notice. Appearance wise, they are very much similar to sinusoidal functions. Their variation is sinusoidal. They are not exactly sinusoidal, but they appear. Sinusoidal, usually their amplitude remains the same as you move from one end to another end, but here you see their amplitude is decreasing slowly as you move from one end to another end. But appearance is somewhat similar to sinusoidal. This is one aspect to remember. And these are not periodic also. Sinusoidal function is a periodic function, whereas this fellow is not periodic. This is one aspect. The second aspect is all the Bessel functions, they start from the origin except one, that is J0. J0 starts at non-zero. The starting point is non-zero 1, whereas for other functions, starting point is the origin. So if you consider any function, anyone, let us say J3, it is becoming 0 at the origin, and also it is becoming 0 at, let us say, 6.2. 3. It is becoming again 0 at 8.9. Again it is becoming. So these are all roots of Bessel equations. Now mixed. If it is given that the wave in the waveguide is a mixed one, then it possesses both Ez as well as Hz. Ez and Hz we have to find out. Of course, we can find out using wave equations as we did in case of TM or TE waves. Hence, in this case, they can be found same as those in case of TM and TE waves. Hence, in this case, fields Ez and Hz and other components also are some of the fields in TM and TE waves. See what this point says is Ez, Hz. Both components exist as the wave is mixed wave. Ez is solved using wave equation. Hz is solved using wave equation involving Hz. In fact, we have solved Ez with wave equation. In case of TM wave, we got certain solution. If we solve wave equation in Ez here also, even here also, we will be getting same solution. Same is the case with Hz also. If we solve wave equation to find Hz in the present situation, mixed case, we get a solution which is same as the solution which we got in case of TE wave. So solutions are same, therefore Ez, Hz are same, therefore other components also are going to be the same given by Ez and Hz. But mixed means sum of Ez and Hz. So field components in mixed wave, they are some of the fields in TM case and TE case. Circular waveguide is considered TM case. This is the field components. It is TM, therefore Hz is 0, Ez is not 0. This is the component which we evaluated using wave equation. In case of TE waves, Ez is 0, Hz is the Bessel function involving Bessel function 1. Before going further, one point is required to be told. In the solution for Q part of the PQ, we assumed solution to be product of two functions P and Q. We applied variable separable method. We arrived at an equation in Q, in P and in Q also. Q is equation pertaining to Q is an ordinary equation. Solution involves sine and cos involving two arbitrary constants, sine and cos. This sum sine and cos, it can be expressed as one sinusoidal function by appropriately selecting the reference. See, if you start the reference in such a way that one term becomes 0, you are left with only one term. That's why you see here in the expressions we have only cos, sine, cos. Other term is absent. Right. That way, two terms, by selecting reference appropriately, we can see that two terms become one, or one term is eliminated. That's why only one term in all the expressions. So these are fields as far as TM waves, TA waves are concerned. Mixed wave, in case of mixed wave, if you add these two, you will be getting field components in the mixed wave. See, in the mixed wave, H rho is this plus this. In the mixed wave, E phi is this plus this. Where is E phi? This. In the mixed wave, Hz is this plus this. Ez is this plus this. In all the modes, notice the field components between the walls in rho direction and phi direction also exhibit standing wave pattern. The field variation in rho direction is described by Bessel function, and phi direction is either sine or cos. This is what I have to share with you regarding circular waveguides. In the second part, what exactly we did is we considered different waves, TM wave first, then TA wave, then we considered mixed wave. TM wave is its field components are found by solving wave equation in Ez. In case of TA wave, field components are found solving wave equation in Hz. In case of mixed wave, field components are found by solving wave equations in Ez and Hz.